In this lesson video, we will be taking a look at distance. So let's jump right into what that means in terms of geometry. In geometry, distance is always a length measurement. Sorry, let me get a pen to write with. There we go. And since distance is a length measurement, it is found using a calculation of using subtraction. It's the difference between coordinates, especially when we talk about distance on a number line. Your distance on a number line requires you to understand that if I put 2 points on a number line has assigned values. So if we think of this as an x-axis, A would be the first x-coordinate we see, so we'll call that x1. B is the second x-coordinate along the line, so we'll call that x2. So the length of AB along that number line is the difference between those two numbers, those two coordinates. So we do x2 minus x1. But because length is always a positive measurement, we use the absolute value of x2 minus x1, which really means that the order of those in subtraction does not matter in this case. So I could do x1 minus x2. And so we're going to apply some of that to these problems. So number 1, example 1, we're going to use this diagram to name the following. First, they say name the point on AD whose distance from D is 2. Well, that means we're only focused on segment AD. And so along AD, D is the endpoint. I want a point 2 units away from that endpoint D. So I can just count and get coordinate B, or point B. But on number 2, they ask you to find a point whose distance from E is 2. Well, E is right here, and it doesn't specify where that is, so we actually have 2 answers. You could have C, that is 2 away to the left, or G, that is 2 away to the right. And we're just counting those spaces to get that. Because on a number line, you can actually count spaces to find length. I'm going to erase some of this to make some room for the rest of these problems. Number 3, they ask you to find the midpoint of segment AE. So if I look at segment AE, the midpoint, you'll remember from last lesson, is the point that splits AE into 2 congruent pieces, the exact middle. We could do that by finding the full length of AE. Again, we can count or do subtraction. -3 minus 1 is actually -4, but distance is always positive, so we take the absolute value. We get 4. So the length of AE is 4, and so I want half of that. Half of 4 is 2. So 2 away from E at the end and 2 away from A at the beginning give us point C as the midpoint. Most of you would probably be able to just look at that and figure that out, but I wanted to give you some explanation. All right, these next few are a little more challenging because we throw in some other fractional values, but we're going to still follow kind of the same pattern as midpoint. So if they want you to name a point that is 2/3 of the way on AG. Well, AG is the entire length of those points given to you. The entire length then is from -3 up to +3. You can count spaces or you can use your subtraction. -3 minus 3 is -6, but the absolute value of -6 is +6. So AG has a full length of 6. I want a point that is 2/3 of the way from A to G. And so you actually have to follow this in order from left to right. Since they list A first, that direction is going to tell you how to get to 2/3. So if I were to divide that full length of 6 into 3 equal pieces, each would be 2 units long. So there's a third, there's another third, and there's a third. This allows me to see that from A to G, the 2/3 mark is point E. The next one of these is going to be very similar. A point that is 1/4 of the way on FB. Well, FB gives us a direction. From F back to B, we're going this way. That has a full length of 4. -2 to +2 is a length of 4. So if I take that 4 and I divide it into 4 equal pieces, each piece is 1. So 1/4 of that length of FB is just 1 unit. So back from F, 1 unit is E at that value of 1. So finally, number 6, the numeric value that is half of the way from C to F. Well, C to F is right there. And that length from -1 up to 2 is a length of 3. Again, you can think of it as 2 minus -1. When we do minus a negative, it's like you're doing plus positive, which is 3. The absolute value of 3 is 3. So that full length is 3. Half of that 3, when divided by 2, is 1.5. So I should go 1.5 from the endpoint, and it puts me halfway between 0 and 1, which is why they want the numeric value. There is no letter there. Well, at that point between 0 and 1 is the letter or number value 0.5, or you can write it as a fraction 1/2. Now, that is how to calculate length or distance on a number line, which a lot of the times you can do by counting. However, this next part is actually a typo. It should say distance not on a number line. We just did that. It should say distance on the coordinate plane, like an XY axis, y-axis, y, and then x-axis, where they meet is called the origin. Your XY graph. The distance calculated on the coordinate plane, we now have 2 directions we can go. Now, that means if our segment AB goes like this, there's A, let me fix that didn't look very good. There's A, there's B. That's a diagonal segment. I can't just count for length there. And in fact, I can't do just subtraction because they are separated horizontally by a certain number, but also vertically by a certain number. They have distances on the x-axis and y-axis. So we have come up with a formula called the distance formula to help us calculate that. The distance formula is this. D equals the square root, parentheses, x2 minus x1, parentheses squared, plus parentheses y2 minus y1 parentheses squared. And that's all under 1 square root. That looks really confusing, but let me give you some pointers as to where this comes from and what we're using. x2 and x1 come from the x values of 2 different ordered pairs. So one ordered pair would be x1, comma y1. That's 1 point. The other point would be called x2, comma y2, because we have 2 different x's and y's. And so we assign that labeling system to each ordered pair, and then we plug those in. What I want you to notice is this parentheses is not an x and a y. It's both of the x's. The other parentheses is not an x and a y. It's both of the y's. So be careful what you're grouping together when you do this. Now, I'm going to tell you where this comes from. Let's say on a graph, let me write with a pen, not a highlighter. Let's say on a graph, xy axes, I had point B over here, point A over here, and I drew that line. You can think of this as the hypotenuse of a right triangle. In that case, this horizontal difference between A and B, so the distance from x1 to the x2, let's just call it A, lowercase a. That's point or measurement, a length of lowercase a. And then the vertical distance from B down to where A is that way is the difference from the y1 to the y2. Let's call that length B. Well, then this is a right triangle. The hypotenuse is always called C. And from a right triangle with sides A, B, and C, you might remember this. A squared plus B squared equals C squared. This is called the Pythagorean theorem. And so that is really where our distance formula comes from. And I'll explain that to you a little bit more later on. So let's do an example using the distance formula. In this problem, it says that if the school is located at -2, -4, and the park is located at -5, 3, how far apart are they? Well, what we need to do then is assign each of these as x1, y1, and then x2, y2. So this first one I'm going to call x1, y1, and the park then is x2, y2. And that's going to help me fill into the distance formula here. So I start off with the distance. Anytime it says how far apart are two things, you're asking a distance question. Distance equals the square root. That first parentheses is the difference between the two x values, -5 and -2. Difference means subtraction. So I do -5 minus -2. When you subtract a negative, remember that turns it into plus positive. And then you take that parentheses and you square it. And then we do the same thing for the y values. Take my y values, y2, 3, and then y1, -4, and find their difference. So I do 3 minus -4, again, minus negative turns into plus positive. And we square that. And then I start to simplify all this, making it easier to look at. The first parentheses here, -5 plus +2 is -3. So that turns into -3 parentheses squared. And you do want to leave the parentheses around that. Plus 3 plus +4 for the y values here turns that into 7 squared. I have to do what is inside this square root completely, all the way down until it's the square root of a single number, and then I can use my calculator. Let's remember that -3 squared here first turns that into -3 times -3, which is +9. And now I no longer need the parentheses. 7 squared is +49. When I add those together, I get 58. And so to find the square root of 58, we're going to use a calculator. And I'll show you how to do that. But that is about 7.6. I've used my calculator, and so that's how I know that. So let me show you how to put that in a calculator. Okay, so as we look at this, you can see I've already done that. I'll clear it out, though. To bring up the square root feature on most calculators, you're going to look for the x squared button. Well, in order to get the x squared button to change to the square root, I have to hit my second or function key, and then x squared, and it brings up the square root. So I type in 58, hit enter, and you get about 7.6. So going back, the school and park are about 7.6 units. That might be blocks, might be miles, we don't know. So let's move on to another example. We're going to do the same problem on part B on the next page, exactly the same, but we're going to use the Pythagorean theorem. So the first thing I need you to understand is from the other page, the school was located at -2, -4, and the park was located at -5, 3. Just taking those same two locations, and we're going to plot those on a graph. -2, -4 puts us right there. So I'll get rid of my arrows. So that's the school. The park is at -5, +3, right there. Get rid of those arrows. And so I connect those and I get this straight line segment. And so to find the distance, it's going to be about 7.6, but I'm going to show you how to find that using the Pythagorean theorem. So here's what we did previously. To use the Pythagorean theorem, you always need a right triangle. So I'm going to turn this into part of a right triangle. It's always going to be the hypotenuse, C. To come up with the other two sides that we call legs, I'm going to pick one point and either go up or down to the next point first. I'm going to go just vertically. Well, if I start at P and I go down, that creates a vertical leg of a triangle, and I stop when I reach the line horizontally for my other point, and I draw in that side. And that creates a right triangle, where this horizontal leg we'll call A, the vertical leg up and down we'll call B. And then I can just count those spaces. A is only 3 spaces long, B is 7 spaces tall. So when I go to use my Pythagorean theorem, A squared plus b squared equals c squared, I can plug in for a and b, which turns that into 3 squared plus 7 squared equals c squared. And you'll recognize from our previous problem with distance that we had a 3 squared and a 7 squared. Even though it was a negative 3, when I squared it, it still turned into positive 9, just like positive 3 squared turns into positive 9. 7 squared is 49. And so to combine those, we get 58 is c squared. Well, to get c by itself, remember, we take the square root of both sides to cancel out the squared. That means c, or the length from the school to the park, is still the square root of 58, which is about 8.6. I'm sorry, 7.6. 7.6. Okay? So we can apply that to other problems as well. Like on number 7, we're told to find the perimeter of our triangle, ABC, given the coordinates 3, 7, negative 2, 0, and 0, negative 4. Well, I need to remind you, probably, that perimeter means the distance around the edge of a shape. But in the case of a triangle, it is also the sum, as in addition, of all sides. And so the 3 sides we're going to have here, you'll see after I graph the triangle, are going to be AB, BC, and AC. So let's plot those points and we'll see what it looks like. A is at 3, 7. There's A. 3 over from the origin, up 7, and you get A. B is at negative 2, 0. So go back negative 2 on the x-axis, and then we don't go up or down. C is at 0, 4. So we don't go left and right. We stay lined up with our y-axis, but we go up 4. Now, this looks like they're almost collinear. They're not. This is a very skinny, narrow triangle. And it looks like that. Okay? What we're going to do is find the lengths of AB, BC, and AC. Because I have this graphed on a coordinate plane, I'm going to use the Pythagorean theorem way of doing this. I'm going to first treat AB as the hypotenuse of a right triangle. So I'm going to fill in my legs vertically and horizontally. I'm going to count their lengths. From B over here to this right angle is a length of 5. Think of it as negative 2 minus minus 3, or 3 minus negative 2. Either way, you get an absolute value of 5. And from A down to B vertically was 7. So A and B lengths, little a and little b, are 5 and 7. So for the Pythagorean theorem, for AB, we're going to do 5 squared plus 7 squared equals c squared. And then we start to simplify. 5 squared is 25. So this turns into 25 plus 7 squared is 49. And then we add those together. 25 plus 49 is 74. So 74 equals c squared. To find c, we take the square root of those. So AB is the square root of 74, which, if I plugged in my calculator, is about 8.6. Okay? So let's move right along and find the length of BC. From B to C, if that's the hypotenuse of a right triangle, I'm going to not try and cross through up and down. I'm going to go out here to the left. From C back that way gives one leg, and then from B up to that right angle now gives me the other leg. There's my right angle. So this horizontal leg is 2. The vertical leg is 4. You can count those. So for the Pythagorean theorem for this one, for BC, it becomes 2 squared plus 4 squared equals c squared. And I just keep simplifying. 2 squared is 4. 4 squared is 16. And then I add those, I get 20. So 20 equals c squared. So I take the square root of both sides, and we get that BC is the square root of 20. Again, when I plug that in a calculator, I get about 4.5. And then finally, I need to find the same length for AC. AC, if I think of this as the hypotenuse, there's a vertical leg, there's a horizontal leg. Horizontal leg is 3, vertical leg is also 3. So the legs A and B are 3 and 3. So we get 3 squared plus 3 squared equals C squared. Those 3 squareds are each 9. So C squared is equal to 18, which means I take the square root of both sides, and AC is the square root of 18, which is approximately 4.2. But again, the problem asks you to find the perimeter. So the perimeter is the sum of those. So I'm going to take 8.6 and add 4.5 and add 4.2, again using my calculator. That gives me about 17.3 for the perimeter of the triangle. All right, this video is a little bit longer, I understand, but I want to really make sure you have plenty of examples. Example 3 is one we're going to omit. We're going to skip this one. It doesn't work out very well. I didn't double check that before I made copies. So we're going to skip it. So that means we can go on to the next page and our last example here. And what I actually want you to do is attempt this on your own maybe. Pause the video, give yourself some time to try and do it, and then click play when you're ready to see the problem worked out. If you need more time, go ahead and pause. Otherwise, this is what we're going to get for example 4. It says that if you're given the coordinates A is at 2, 4, B is at 1, negative 3, and C is at 0, 0, D is at 2, 2, and E is at negative 3, negative 1, and F is at 0, 2, we should be able to put those segments A, B, C, D, and E, F in order from shortest to longest. And so that means we need to find those separate lengths. Okay? So we're going to use our distance formula since I didn't give you a graph. I don't want you to take the time to graph it if I don't provide a graph for you. We're going to use the distance formula. I'll remind you what that is. Distance equals the square root, parentheses, x2 minus x1 squared, parentheses, y2 minus y1 squared. And so that allows me to set up A, B, C, D, and E, F. For AB, the x's are 2 and 1, so I'm going to subtract those. 2 minus 1, I can use that order too, squared. And the y's are 4 and negative 3, so I'll do 4 minus negative 3. Again, that turns it into plus positive. Okay, 2 minus 1 is 1, 1 squared is 1. 4 plus positive 3 is 7, 7 squared is 49. So this is the square root of 50. Now, I'm not going to even evaluate that into a decimal. I'm going to leave it as the square root of 50 just for the sake of comparing it to the other lengths. Saves me a little bit of time. For CD, the x's are 0 and 2, so I would do 2 minus 0 squared. The y's are also 0 and 2, so it's also 2 minus 0 squared. Each of those 2 minus 0 is just 2, and then I square each of those. 2 squared is 4, plus another 2 squared means it's plus 4. 4 plus 4 is 8, so that's the square root of 8. Obviously, the square root of 8 has to be less than the square root of 50. Same idea for EF. Between E and F, the x-coordinates are negative 3 and 0. So if I did 0 minus negative 3, that turns it into plus positive. And the y values are 2 and 1, so I would do 2 minus negative 1, turning that into plus positive. That ends up being 3 squared plus 3 squared, or 9 plus 9, which is the square root of 18. Now, as I look at these, the shortest segment then should be CD. The next segment would be EF, and the longest segment is AB. If this video has gone fast at all, remember you can pause, go back and replay, but you should be ready to start the assignment for lesson 1A.5.